symmetric space of non-compact type. This corresponds one-to-one to connected simple Lie group. There is a one-to-one correspondence. Connected, simple, I mean center free. So in this correspondence, H2 corresponds to PSL2R. And Hn corresponds, those who know if you took a course in Lie group, to PS O, N, and 1, and so on. There is a one-to-one correspondence. So if you give me a symmetric space, X is irreducible, it will correspond, the Lie group will be just the isometric group of X. Then take an identity component. This is the correspondence from here to here. Vice versa, if you give me G, which is a simple Lie group, and K is the maximal compact subgroup, and it's known that there is only one maximal compact subgroup up to conjugation, then X will be, at least as a set, G mod K. G will act transitively with compact stabilizer on X. X will be G mod K, and I didn't tell you what is the metric here. At some point I will discuss symmetric space and define it. There is a way using the killing form of G to define a canonical metric here, which makes it a symmetric space. So there is one-to-one correspondence between these two categories. And this is an important set of Riemann manifold. For instance, it includes all hyperbolic manifold, real hyperbolic, also complex hyperbolic, also quaternionic hyperbolic, and so on. But it also includes other type of manifold. Let me just.
Sachi, you need to take the connected component there, the SON one.
P, so it's still not connected.
SO21 is 2-to-1 correspondence with H2. If you take SO21, then it's 2-to-1 correspondence with H2.
I take ON1. Okay, I'm not sure. Okay, maybe you're right. One of them identify 1 and -1, and the other takes the determinant and still not connected. Yeah. I think if you write ON1, then there are 4 components, but okay, I don't mind so much. Yeah. So here is another example of what? Okay. Another example of. By the way, the isometric groups of X will always contain the connected component of infinite index. So it's almost the same group in general. Another example, if you take G to be SL3R, or SLNR, I could take it, and then the symmetric space X will be as a set. I can identify with SL3R modulo SO3. The maximal compact is the orthogonal transformation, and this is a 5-dimensional symmetric space, and it's different nature than hyperbolic space. Because in hyperbolic space you can find geodesic, but you cannot find flat planes. Here you can find flat, embedded, totally geodesic planes. In a hyperbolic case, the group for isometry acts transitively on geodesics. Here it doesn't, but it acts transitively on flat planes. So So in a sense, the geometry here is much more rigid than the hyperbolic geometry. And this is why there are so many rigidity theorems for this group and lattices in this group, which are not applied for hyperbolic groups.
Flat plane is just Euclidean space.
Sorry?
Flat plane is just Euclidean space.
Flat, yeah, I will describe in more detail symmetric space at some point in the course, but yes, flat plane, I mean flat Euclidean two-dimensional plane, which is totally embedded. If I take SL4R, then I would find flat three-dimensional space inside the symmetric space. And this is somehow the reason that there are so many rigidity terms that I will sketch in a moment.
And it's easy to see one?
What? Easy to see what?
One flat plane.
Yes. Yeah. It's. But I will speak about it. Now I want to give an overview of the theory. I just want to tell you, so there is this correspondence. Now if you fix x, given x and g, there is a correspondence between, say, let's just make a definition, an x manifold is a complete Riemannian manifold locally isometric to x. So at any point you have a neighborhood which is isometric to a neighborhood in x. But this is equivalent to say that it's a manifold of the form M x mod gamma, where gamma is in G, the group of isometries. G is just a connected component, so yeah, let's do that. And in the group of isometries, and it's discrete. Torsion free. There's no torsion. Why I don't want torsion? Because I want it to gamma acts freely, and then I can look at the quotient manifold. If there is torsion, every finite subgroup there is a fixed point. We will see it at some point. And then if I look at x mod gamma, it will not be a manifold. It will be an orbifold. But then I will call it an x orbifold, which is still okay. So there is a one-to-one correspondence between x manifold of finite convolume and torsion-free lattices in G. Or more generally, there is a one-to-one correspondence. There is one-to-one correspondence between the set of lattices in G in, say, let's say, in the isometry group of X, which is almost G, and the space of X orbifold of finite world. More generally, there is a one-to-one correspondence between discrete subgroup of G to X orbifold, and it sends lattices to those of finite volume. And if you take here torsion free, then you will get here a manifold instead of orbifold. But any orbifold, there is a finite cover which is a manifold. We will see all these things later. So in a sense, to study all the lattices in a given group is the same as studying if you prove a theorem for all the lattices in SL2C, you prove a theorem for all hyperbolic tree manifolds. SL2C is the group of isometries of the hyperbolic three-dimensional space, and there is a one-to-one correspondence between the lattices there and finite volume hyperbolic orbifold. And this is a very popular area of mathematics, two-dimensional hyperbolic manifolds, or in general hyperbolic manifolds. So this explain this correspondence. Maybe now it's time to have a break. After the break, I will tell you some of the classical theorem, like rigidity theorem, arithmeticity, Dan-Margulis theorem, and so we will have another hour and 7 minutes after the break. But let's try to move to a nicer class with bigger board and yeah.